So what can we do? Well, I think we're all used to Moore's law. Maybe it died a while ago, but it creeps on. Have patience. Wait a year, wait 2 years. Maybe the computer will be bigger. On the right is the current record-breaking supercomputer at Oak Ridge. On the left is the IBM one from just 2 years ago. And last year it was one in Japan. They get bigger and bigger and better and better every year. So, you know, it's not the worst strategy. It's just wait. And it's because these problems are so galactic scale that we can't necessarily wait. And so we start looking for other ways of making these problems useful. And these are just some examples. On the left, in fact, that's an IBM chandelier or cryostat. The actual chip is about the size of a quarter. It's just right above that golden can at the bottom. That actually is gold, by the way. This is one of our atomic prisms, and that's an ion trap machine. It's not shown to scale. The chandelier is about this big and about 4 foot high. I'll just show you an idea. All right. So we're going to try to emulate nature here. Nature is the biggest computer in the universe by definition. All of the data are all of the quantum particles. We put them all together. We do things in a sensible way, and the apps, and the results of the apps are us and everything around it. And nature works at that level using quantum mechanical principles. And that's the whole point of quantum computing, is to work the way nature works, because it's really good at doing really hard problems, right? Like the universe. I mean, it's a trivial sort of observation, but if we can do that, we may be able to apply it. It's a completely different paradigm. It is not classical coding 2.0. It's completely different. Your best classical coder in the world could be a really bad quantum coder programmer as well. They're completely different programming models. And it hurts your head, and you get things wrong for a long time. When you get into this, you start seeing weird circuits like this thing. And there's been a huge learning curve. There's been so much that has gone into the education of people to learn about quantum computing. But I will tell you, there are easily more than 100,000 people out there who know how to program quantum computers at this point, right? Just the combined efforts of many companies. The problem is the quantum computers are still too small. They can't solve any of these problems yet. All right, so how do you actually build one? Well, you decide on a quantum bit technology, atoms, ions, superconducting, silicon defect vacancies. Somehow, you emulate the way nature does this basic unit of information. You manufacture, you find them, you control them. I tend to split this between the semiconductor approaches, the manufactured, and the so-called natural approaches, which are the ions and the atoms and the photons and things like this. All right, so you arrange them some way into a chip. You create a QPU, not a CPU, a QPU, a quantum processing unit. Then you start controlling them. In our case, lasers, same with ions and photons. In the case of superconducting, it's microwaves, how you do this. I'm highlighting these 3 words not to explain what they are. It's just people keep showing them, expecting everyone to get really excited about them, right? Superposition, it's this weird thing like 0 and 1 at the same time. Entanglement, spooky action at a distance, that's what Einstein said. And then interference, here are the waves. Somehow you're doing this weird computing things with intersecting waves to get the best answer. I'm really literally waving my hands here, but these are part of the fundamental coding principles about how to do this. And then you run it, and you hope you get the right answer. Now that's a little bit of a change if I say, wouldn't it be nice if I got the right answer? You know? Probability is core to this technology. Probability is core to quantum. So unlike a lot of what we call deterministic ways of computing, I do this, I do that. If this is true, I do this. Otherwise, I do that, right? That's traditional programming. Quantum computing is very, very much tied up with probability. And that's what drove Einstein crazy. He could not deal with that. When he said that God does not play dice, that's what he was referring to. Stephen Hawking responded, evidently God plays dice constantly every chance he gets, because that's what quantum account. They weren't speaking in a religious sense. They were speaking very high. All right? So we're not going to replace classical computing with quantum. We're going to use them together. We're going to use them on 3 classes of problems. The examples, primary examples, are machine learning, right? Once they're big enough to actually do something with the data, to do certain types of optimizations and simulations, and computational chemistry. The early money is going to be in chemistry. Everything else is going to take much longer. So in that regard, if we think of chemistry, if we think of materials, how does that relate to what you are doing? Will quantum computers be used to create better materials to make better quantum computers or better components and things like this? All right. So this is a little bit about super tech, financial portfolio optimization, load forecasting in grids on networks, in data centers, and network simulations. And that's related to chemistry and machine learning here. Okay, so I'm just going to end here with a few caveats on, related to this. The biggest QPU anyone has right now is IBM's at a little bit more than 400 qubits, right? So it's one chip, 400 qubits. They're very proud of it. They should be proud of it. But we need 500,000. Other vendors talk about 20 or 32 or 65. But we need 500,000 to be able to do anything better than what we can do classically. So we're worrying about this point where quantum computer will do better than classical, right? We're not going to do the same sorts of things. So, somewhat extreme point of view, the quantum computers we have today are toys compared to what we really need. Just, you know, there's nothing you can do. You can learn. You can experiment. That's great. Do that. But you can't put that into a business and say, it now solves new problems. And therein lies the rub of what we have to do here. All right? And so when it comes to transportation, here's my analogy. I need to get to Europe. Well, let's put it another way. I need to get down the street. My bicycle is fine. I need to get to Europe. My bicycle's not fine anymore. Okay? I need a completely different sort of technology to get there, and one that's far more sophisticated. So now we're talking about systems, and we're talking about ways of scaling these things. And one of the ways of scaling is to break encryption. And this is the big, scary thing that people talk about. So just as I mentioned about, you know, the size of today's quantum computers, to break encryption, the currently best estimate is 20 million qubits. We have at most 400. Are you really scared encryption is going to be broken tomorrow, right? Are you running for the hills, right? You should be securing your data. You should be using the most modern encryption protocols. But you hear about this 75% of the time when you hear about quantum computing. And this isn't going to happen for years and years and years. It probably will happen eventually, but not for years and years and years. All right? So let's kind of finish up here with some networking and some photonics here. Since we can't make a single QPU big enough, we're going to need more than one. Right? If I can only fit 100 or 400 or even 1,000 or 10,000 qubits in a QPU, I need more than one to get to 500,000 or bigger. You know, that's 500,000 is just the low number, right? We're going to need more of that. So somehow we have to go to more of that, and we have to connect them. And unlike the circuitry that's in your phone or your laptop, it's not electronic circuitry. It's quantum circuitry. We're not necessarily running electrons between these things, right? In some cases, particularly the superconducting approaches, we can use microwaves. But in all the other approaches, these connections are going to be photonic. So you imagine a single device that may use, in our case, photons to control it, to do everything it should be doing, and then to connect to get bigger systems with photonic quantum interconnects. It's another opportunity there. It's very hard to do.